Hello everyone, this is Tammy. Today I will talk about the paper Experimental Quantum Teleportation, published on Nature in 1997. In this scenario, Bob wants to change his photon to be exact replica of Alice's photon, or they want to pot this photon. What about Alice send the measurement to Bob? Then Bob can rotate his photon to the thing. However, this is impossible because of the non-cloning thermal. A team of physicists in 1997 found that a particle's quantum state can be transformed to another via entanglement, and this process is what we call quantum teleportation. To see this, I will talk about today. It is the first experimental verification of quantum teleportation. It demonstrates how to generate entangled photon, achieve quantum teleportation, and verify its success. Let's look at the concept of quantum teleportation. Photon 2 and 3 are entangled, emitted by EPR source. Photon 2 is sent to Alice. Alice has another photon 1 wants to teleport. Alice measured it jointly with photon 2, and this process is called build state measurement. This measurement will give 4 different outcomes, which will affect Bob's photon. Make it correlate with the measurement results and photon 1's original state. In the end, we transfer photon 3 using the classical information getting from Alice's side to make it to be photon 1's original state. On the one hand, Bob has to wait for the classic information that can travel no faster than the speed of light. In this way, Einstein relativity is established. On the other hand, photon 1 loses its original state, and we have no information about the polarization of photon 1. So the teleportation process thus clearly adheres to the general principle of quantum measurement and quantum non-cloning thermal. Let's look in the theory. Photon 1 is an arbitrary polarization. Photon 2 and 3 are entangled. They could be in any of the 4 build states, which is a maximally entangled state of 2 qubits. We want it to be in this build state. This is a full wave function for this 3-particle system. Photon 1 and EPR pair are in a pure product state. No classical correlation, no entanglement. Now we implement build state measurement, which is performed onto the basis of build states. We can rewrite the full wave function into this. The 4 measurement outcomes are equally likely. Each has probability 25%. If photon 1 or 2 are detected in 5+, and photon 3 must be in the state of this. And don't forget, we want to transfer photon 3 to the original photon 1 state in the end, which means we need to apply an unitary operator on it. And this is the input state. This is the output state. We can calculate the unitary we want. Apart from calculation, we can get the required logic gate very easily. For 5+, we need to flip the phase, which means Pauli Z gate is required. For 5-, we can see bit flip is needed, which leads to Pauli X gate. For Psi+, we need both split flip and phase flip. That is Pauli XZ gate. The last build state is a special state. It's the only build state can be detected. Right now, photon 3, it is already in the original photon 1 state. In conclusion, once particle 1 and 2 are projected onto Psi-, photon 3 is instantly projected into the initial state of particle 1. Now let's look at the real experiment. to see how the psi minus can be detected and why it is the only one. Here, in the middle, it is the EPR source. Entangled photon 2 and 3 emerging from type 2 spontaneous parametric down conversion. Photon 4 here is used as a trigger. When it's detected, confirm that photon 1 has been sent to Alice. Photon 1 here passed through a polarizer. We can orient it as we want, and also it can make photon 1 to be an independent photon. Alice combines photon 1 and 2 using a beam splitter to perform a build state measurement. One important condition is that photon 1 and 2 must be indistinguishable. To achieve that, we need indistinguishable in arriving time, pulse pumping and narrow beamwidth splitter. Once they are indistinguishable, quantum interference will take place. Now we come to the most important part. For 4 build state, only psi minus is the antisymmetry state. Others are all symmetry state. Only the antisymmetry state can lead to the coincidence event happen. The coincident event means the 2 photons can reach the 2 detector at the same time. For other symmetry states, there's no coincident event happens. In summary, once both F1 and F2 detect the photon, particle 1 and 2 are projected onto psi minus, which means particle 3 is instantly projected into the initial state of particle 1. Let's see how to verify the quantum teleportation in the experiment. Photon 1 is polarized at 45 degrees. Photon 3's polarization is analyzed using a polarizing beam splitter, which selects 45 degrees and minus 45 degrees. Adjust the mirror to resize the path length difference, which could be referred as delay. These 2 pictures are theoretical prediction and experimental results for the 3 found coincident probability. Upper 2 pictures means F1, F2, D1 detector clicks. Under 2 pictures are F1, F2, D2 clicks. The green part in theoretical pictures in the middle means quantum interference occur, and photons are in the region of temporal overlap. When quantum teleportation happens, the probability of F1, F2 clicks is 25% because of the 25% psi minus build state. Photon 3 has all become photon 1, 45 degrees. So 0 for D1. Do a multiplication. We can see on the upper picture, in the middle is 0, and the down one in the middle is 25%. Outside of quantum teleportation, F1, F2 click for no quantum interference. That is 50%. Photon 3 has no correlation with photon 1, so they are both 15%. Do a multiplication again. On the 2 picture, they are all 25%. Compared with the experimental results, we find it is correct. In this paper, this group of physicists also examined different polarization of photon 1. They even used the circular polarization, and they got the expected experimental result. In summary, the experiment successfully achieved quantum state teleportation of a single photon and verified it. The long-distance transport of quantum state without annihilation is a key technology for developing communication. Quantum teleportation enables remote information transfer, benefit the quantum computing and quantum network. This is the end of my presentation. Thank you for listening.